let's start. We had a last-minute switch. Unfortunately, Megan not feeling very good. We switched to her talk to the last one of the day. We hope she's going to make it. We're going to keep you updated. So please welcome on stage Benedikt Terhechte, correct?
Yeah.
Yeah, good. Which is going to talk about associated types. Yeah, okay, cool. Thank you very much for being here. And I hope you're going to enjoy the talk, because we already had a long discussion about this during a conference in was Verona last year, the Prague, yeah, during a lunch. So I really loved some of these ideas, so I hope you're going to enjoy them too. So listen to him and cheer him on the stage. Thank you.
Okay, hi. As you can see, there's quite some animation going on, and that was so that I could please you a bit, because I will actually give this talk in GNU Emacs, the text editor, and that is not well known for its animation capabilities. So these are all the animation you will see today. Okay. Let's go to text. I'm talking about protocols with associated types, when to use them, how you can avoid their pitfalls. A short bit about me. I'm Benedikt Terhechte. Some of you may have read about some of my writings on adventure.me, which is a blog, or on Twitter, which is @Terhechte. I'm also a developer at Xing, which is a German company doing something like LinkedIn, but mostly for the German-speaking markets. You may also know me by a bit of what I do in open source. There's Hirundo, which is a free mailing list reader for the Swift Evolution mailing list. It's not open source, but it's for the community. If you want to follow Swift Evolution but don't want to actually go into the mailing list and assign it with your newsreader, you can use that, which is an app which basically just does it for you. And there's called Value, which allows you to use value types with core data. Let's start with the actual topic, protocols. Most of us love protocols. You can use them with protocol extensions, with lots of different things. And so when your product guy comes with the problem that he wants that everything in your app has to be bookmarkable, you think protocols. So you can basically make a protocol bookmarkable, and you can basically create a struct user, and it has bookmarks, and everything like a message or a text or a user, everything can adopt or conform to the bookmarkable protocol, and everything is fine. This code runs perfectly. And then at some point you decide, well, I would like to also have this to be equatable, because I want to compare my bookmarks. And so what you do is you add the equatable protocol to the bookmarkable protocol, and then you can execute that code. And what happens is the compiler says, oh, hell no. Bookmarkable can only be used as a generic constraint because it has self or associated type requirements. And you say, what? What's happening here? What does that mean? This is like literally one of the worst error messages you can have for something that everybody kind of wants to do in Swift. And so what's happening is, let's have a look at equatable. And equatable has a function that receives two parameters, left-hand side and right-hand side. And they're both self. And self, in this case, is an associated type. The compiler doesn't really know what it is until everything is compiled, until you actually tell it what kind of type it is. So before we go into detail to see why this associated type doesn't allow you to use equatable, let's first remember that Objective-C, that Swift has three different protocols. You have Objective-C protocols, which are the ones that you use when you want to interact with Objective-C. You have Swift protocols, which are the ones that you use kind of all the time when you have a Swift-only code base or only for within your Swift code. And then you have protocols with associated types, which you probably don't use that often. How do you introduce associated types? The first one is a direct associated type, which is basically a associated type keyword with a value. And this basically says the system that you want to introduce an associated type into this protocol. The second one is a indirect associated type, which is what happened to the equatable protocol, because what it does is you tell it that you have a function, and this function has a parameter, and that is of the type of the protocol, self. And this also introduces associated types into the protocol. And finally, there's another indirect associated type, which is a builder, which is a variable that is of type of the actual protocol. So in these three cases, when you do that, your protocol will suddenly have an associated type if you want it or not. However, if you have a function that returns the type of the protocol, you're not getting associated type. So in this case, you're fine, and you basically have a normal protocol that you can use in the normal ways. So to recap, when setting them directly, when you have them as a parameter to a function, or when you have the type as a get or set variable, that's how you introduce associated types into your protocol. Usually when you use protocols, those are the things you can do with them. So you have a protocol example, and you have a struct called an_example, and it conforms to the example protocol. And then you can say you have an array of example types, or you have just a single example type, or you have, for example, a function that returns an example. And all this is pretty cool, and that's how we use protocol types all the time. But if you add an associated type to the protocol, what happens is, again, compiler says no, because then in all these circumstances, you cannot use the protocol as a type anymore, because obviously it lacks the type information of the associated type, as we've seen earlier. Because what happens is that as soon as you add an associated type to the protocol, it makes the protocol an unfinished type. Protocols in Swift, if you follow the documentation from Apple, are full-fledged types. The documentation basically states they can be used anywhere a normal type like int can. But if you add an associated types, it's unfinished. It's a half-finished type, and so you cannot use it in all variations because the compiler doesn't really know what it is. So what does that mean, unfinished? Why doesn't it know what it is? Let's go through a very simple example. We have a protocol example, and it has an associated type. It has a function value, and this returns something of this associated type. And we have a struct int example that returns 1, and we have a struct string example that returns a string. And then basically we tell it that they are both of type example here. This obviously doesn't work in Swift, but if we would do that and then we want to execute it, what happens here is that we are trying to add the int and the string value, which doesn't work, right? They're two different types, and that's the problem basically with associated types when you don't tell the compiler what it is. The actual compiled program contains, for each protocol that has an associated type, in all the incarnations, different types. They may not be compatible. So one protocol implements a string, another one implements an int, and you cannot use these together. So let's see how to use protocols with associated types. We are going through a simple example just to get a feeling for how you use them. We define a protocol. It's called my collection protocol, and it has two associated types. You can obviously have multiple of these, and we are going with one. And then there's a function at index, and basically you give it an index, and you maybe get an element back, which is of this associated type. And the index can be int, but basically it's also an associated type because maybe your index is something else. And if you want to implement it, you have a struct my collection, and it basically implements the protocol. And we are, in this case, we are explicitly adopting the protocol, which means we are using a type alias to tell the compiler that the associated type element is a string, and the associated type index is an int. And then we have our function, which basically can return the proper thing. You can also implicitly adopt the protocol. In this case, you're not giving it the type alias, but the compiler figures it out itself because you're implementing the addIndex function, and associated type 1 is an int here, and associated type 2 is a string here. So it knows, in this case, the index is an int, and the element is a string, and it figures it out itself, so you don't really have to give these type aliases all the time when you have functions that actually allow to do it implicitly. And once you have an associated type, so once you have a type that implements an associated type, you use some like generics. So here we have a table controller class, and basically it receives a collection, and this collection is of type my collection, which is the actual protocol. So and then you can actually use the protocol name. So let's go back. Here the type is my collection protocol, and basically that's what you hand in. Now at this point you might wonder, why do generics have this syntax and protocols have this? We've seen generics, and generics basically allow you to do to hand in the types that you want for the generic type as element and index, and protocols basically have this weird associated type syntax, and that's weird, right? Why did the Swift designers use generics this way, but for protocols we have to use it this very different way. Why can't you just use the rectangular brackets also for protocols? And let's, for a minute, imagine that Swift would support this. So let's imagine we hack the compiler and we add the ability to have generic protocols. So we create a function for our myCollection protocol that has two associated types. And in this case, the function is called sum, so it just sums up everything in the collection. But since this is a generic protocol now, we have a type element and a type index. Remember, those are the associated types we had. And those types have to be handed into the collection because they are not part of the type anymore. They are generic types now. So that means our sum function also has to explicitly tell the system what are the associated types for the protocol that I'm using. This doesn't look so bad. But once you have more of these, it already looks a bit more difficult because now you have lots of places in your code base where you're always explicitly stating types and you're forwarding basically these types into the actual function. But that's still fine. But the problem appears once you add an additional associated type to your protocol. Imagine you're now adding a iterator type to your protocol. And what happens is you have to go through your code base and you at every instance where you use the other two associated types, you now also have to add the additional one and forward it into the actual using of the type. And that makes it a bit difficult. And here's an example from Java, which had no associated types like thing a couple of years ago. This is Java 1.3. And there's a breadth first search. And as you can see, this is kind of elaborate because all these types have to be forwarded and passed in, and this is difficult to read and very complex. And when you have associated types, what you can do basically, you can hide some of these types within protocols, within the types that you're actually giving in, making it much simpler. So here's an example of basically how the collection works with associated types. You just add the collection, you say it's an element index iterator, and you give it to sum, min, max, or find in this example, and that works fine. And the types will not bleed out throughout your code base and mess up everything as soon as you change the protocol. So this is one of the advantages of associated types. What I have to add here is that other languages, particularly Scala, we've seen Martin Ruderski earlier yesterday, they actually offer both. So they allow you to define associated types on a protocol or generic types on a protocol. So that kind of gives you the best of both ways. Swift doesn't do that, maybe in a future release, but I don't think that it's currently on the roadmap. But what if you run into associated types because you really need some of the functionalities, but you just want normal protocols? So equatable is one of those examples. What if you have a type that you want to have equatable, but the problem is that you really want to use it like a normal protocol? And there are a couple of solutions that you can use here. The first one is you can use an equatable property instead. So you can take a protocol and you can basically define a type on the protocol that is actually comparable or equatable. And then what you do is you basically go through the, when you want to sort it, for example, you basically use the identifier instead of using the actual type. Another thing that you can do is you make the actual types equatable and not the protocol itself. So in that case, basically, you know that whatever you have can be compared because it's the actual type and not the protocol. Another thing that often happens is that you need the associated type only because you need some sort of generic type on the protocol. And in this case, we have a protocol called validator. And this validator has an associated type. And this associated type basically is just used to validate something coming in and giving out the bool, whether it's valid or not. And instead of doing it this way, what you can also do is basically add the type as a generic type into the function, and this allows you to still use the validator protocol, but not depend on any associated types. Another thing that you can do, and this is like a sledgehammer that you can use all the time when you end up with associated protocols where you don't run where you want them, but where you also want to use them in normal situations, is to shadow them behind another protocol. So we have a normal protocol here. As you can see, it doesn't have an associated type. And this protocol has just one requirement, which is a variable, any value, which just returns any. And then we have another protocol. This is our example protocol. It conforms to example protocol. And it just has an associated type here, which is value, and it can return this value. But it also conforms to example protocol here by implementing the any value var and returning its own value as any. And when you do that, we have two structs here, both implementing the example protocol. And now basically, since by adopting example, which also already implements the example protocol, what we can do is we can create an array of different types, even though they have associated types in them. So int example has associated types based on the example protocol and string example too. But since we are hiding them behind this shadowing protocol, let's go back for a minute. We are hiding them behind this protocol here. Since we do that, what we can do is we can actually add them to an array. And by doing that, we can iterate over them. And at runtime, we can do a dynamic cast to basically check out, is it an int or is it a string, and handle it accordingly. So what we do in this case is we use the associated type, but we use the runtime functionalities of Swift to handle them correctly. The final example of what you can do is the one that Apple also uses in its standard library, and it's type erasure. Type erasure is a bit more difficult, but in the end also a fairly simple thing once you understood the basics. What it does is we define a protocol. Once again, it has an associated type value. And it also returns the value. And then we have a struct int example, and this one implements the example protocol and returns a value. And the next step is that we have a struct which has a generic parameter t and conforms to the example protocol that we defined earlier, to this one. And the conformance happens because we have a value function which returns t, which is basically the generic type that we entered into the protocol. We also have an initializer, and this initializer receives another type which also conforms to the example protocol, which is called u, and this type receives we have a constraint here that basically says that the value of u has to be the same as the value of t, which we are entering into the associated type here, into the struct as a generic type. And by doing that, we can basically save the closure, which is from the type that implements the example protocol as a private closure here, and call it when the actual wrapping struct, the any example, is called. This looks a bit difficult, but what we really do is we just wrap one type implementing a protocol with an associated type into another type, into a struct that basically conforms to the example with the associated type. And by doing it this way, what we can do is, and this is what Apple does a lot, because when you look at the standard library, you see there's an any collection and an any sequence, and they really just work this way. By doing it this way, what we can do is we can create an array of items, and they are basically different types that all conform to the proper protocol for a specific type, but they are still in one array. And so whenever you need to get rid of the types for a protocol with associated types, you can use type erasers. Now this was a bit difficult, and this is also something I doubt you really want to use, but if you want to use it, there's lots of documentation for that. And now let's do something much easier and much more interesting, see how we can actually leverage associated types. So what can we do with associated types that we cannot do with protocols, for example? And let's start with something simple. We can use them to constrain our types to tell the compiler that some of the things that we want to do are not allowed, to make sure that any wrong actions basically can be called at compile time. So in this case, we have a protocol called action type, and we have two different actions called electric action and water action, and they're both of type action type. We also have a protocol collectible, and this collectible is everything that can be collected basically, and it has an associated type called action that once again is of type action type, and we have a function called act, and what that does is it takes two different types implementing the protocol, and they act on each other, so one on the other. And what we do is we make sure that the action, the associated type, is the same for these two types. And based on this constraints that we say only types which always have the same associated type, what we can do is, I know nothing about Pokemon, but I did a bit of research here. And so apparently Pokemon have different actions. So there are electric actions and water actions, and there's a Pokemon called Raichu, which I never heard before, which is an electric action, and there's Wartortle, which in my mind is the perfect name for something, has an action called Action Water. And by defining these three structs, which all implement the collectible protocol and defining the type to be electric and water, we can now go on and they basically fight each other. We create a Pikachu here, we create a Raichu, we create a Tortle, and we tell Pikachu to act on the Raichu, and they both have the same associated type, which is, I think, electric, and that's fine. The compiler said, no, that's not a problem, but when we try to tell Pikachu to act on Tortle, the compiler will actually tell us that this is not possible. The error message is awful. It will say generic parameter other cannot be inferred. But basically, that's what it does. It tells us this is not possible because the types don't match up. And by doing this, you can create different types in your software that actually make sure they are only used with certain other types in a very simple way. Another thing you can do is define for your types custom interfaces that allow you to use them in a very general way. Here we have something called network searchable, and it has one associated type called element. And it has a static function. It's called search, and it receives a session and a query, and it returns a promise with the elements that is the search results in this case. And then we can create a controller, and this is basically a search controller. Now everything here is very simplified, but what we do is we tell it that the controller uses a type which conforms to the network searchable protocol, and it receives a resource that actually conforms to this type. And then we basically take this resource and call search on it with the session and the term and handle the results. And by doing that, we can take, let's say we have a struct user here and it is a network searchable and it implements the proper search functionality, so it adopts the protocol. And then we can create different controllers for different types and they all work correctly because they implement this associated type in the right way and the protocol in the right way. And this allows us to write very generalized code that you only write once and then use with multiple different types in your code base. Another thing that you can do is use them to make sure that certain things align. And for this, I created a validator protocol, which is also a very simple example here. You have a validator, it has an associated type, and it has a function validate. And this function takes an input of type I and returns whether it's valid or not. And then we take a email validator, which is of type validator, and it is the validate function. And what it does is I wrote very complex email validation code here. It just checks if there's a @ sign in there. And I also wrote even more complex code to validate, to write a name validator, which just checks basically if it is empty. And these two structs, they conform to our protocol. And finally, we have something called a value, which is a value that you call with the proper validator conforming to the protocol. And it basically calls on the validator the validate function. And it also receives a value when you initialize it. And this value is the associated type of the protocol, which is validator point I in this case. And by doing that, what you can do is you can basically create a email value, for example, here, which is of type email validator. You give it something, and then it will correctly do the valuation, the validation. And the same here, you create a name validator, you give it something, and you do the validation. So this makes it easy to write validation code as properties in your code base, which can be used throughout the code base and are all based on the same protocol, which is the validator protocol. Finally, I have a demo, and for this demo, basically, I'm I'm trying to go through a very simple problem, which you have in certain apps all the time. So the problem here is, now this is a Mac app, but the very same thing can be do for iOS, and this is just as an example. So the problem is you have a user interface, some sort of UI. It's a sidebar, for example, where the elements in the UI, they all interact in a very specific way. So when I click this button here, something appears here and disappears again. And when I select this pop-up here, down here something should change. So there are lots of relations between the elements in this sidebar. And this is only a simple example, but it could be much more complicated. And when you consider how you would implement this, then you could do it with a UI collection view, for example, an interface builder, or with EB outlets, and you would need to create a lot of relations and combinations between these different cells. And that makes it kind of difficult, especially to make once it's very complex. And there is one design pattern, which is also used by ReSwift, which is the reactive programming pattern, that actually what it does is it just defines a state, which can be a struct that contains all your application state. So basically you would have whatever you enter in the search bar here, is this button pressed, is it not pressed, what has been entered in here. All this data is just stored in one struct, and then the whole UI basically just resolves around this data. Whenever the data changes, the UI is rebuilt. And there are a couple of frameworks that do that, like, for example, ReSwift, which is a Swift implementation of reactive programming for this particular case. But maybe you don't want to introduce another dependency into your code base. Maybe you don't want to add ReSwift just for this particular use case. And given the power of associated types, we can actually model the very simple idea behind this in around 20 lines of code. So we are going to develop a very simple example that you can actually introduce in your code base to use this reactive approach for only a part of your code base, but not for the whole code base, so that you can just use it at some spots where it's actually necessary. And we are using associated types to do that. So let's have a look. It all begins with a very simple protocol. It's called form state protocol. And this is just an empty protocol which allows us to tell the compiler that certain constraints apply to types conforming to this. So we don't have to do anything with this. The next one we have is another protocol. It's called form cell protocol. And this one is the actual cell that we are trying to use to model the user interface, the UI. And this cell has one associated type, which is called state. And this conforms to form state protocol. And this basically models the whole state of the UI. Basically everything in the UI, like what has been typed into the search bar, which button has been clicked, is modeled in this state. And then there are two methods. The one is setup cell, which is called once to tell the cell that is being displayed on the UI now. And the other is state updated, which tells the cell that the state has changed, that the UI should properly update itself. Then we have something which is a store. That's how I called it, and it's very simple. It's defined for a specific state that conforms again to our form state protocol, and it keeps this state, which is the application state that we talked about earlier. And it has a list of subscribers. And these subscribers are really just closures that take a state and do nothing with it, and they use the state to update their UI. It's initialized with the state, and then you apply the state and store it in here. This basically is a single point of truth for the state that we have, that the form holds. And then there's the apply function, and this is kind of where the magic happens. What this does is it has a closure which receives the state, and you mutate the state, and then it's taken back in, and all the subscribers are then specifically updated with a new state. So it's very simple, basically. We take a mutating variant of the state, we apply the changes that come in with the closure, we store the state again, and then we take all the subscribers and we tell them that the state has been updated by basically just calling the closure with a new state. Finally, when a new cell has been created, when we want to add a cell to the UI, what we do is we can subscribe it. And what that does, it basically just takes the state updated method from the protocol, remember the protocol has a function state updated, and we are basically just taking this and adding it to the subscribers, and finally we call it once so that it gets the initial UI state. Then this is really just UI stuff that we can basically ignore. It just sets up a NS stack view and a NS view, which are the very same things as on iOS, just with 2 different letters. And then there's a function called addCell that receives a new cell that conforms to the form cell protocol. And we are making sure that the state, the associated type of the cell, is the same as the one that we have here, the one that actually is part of the store, so that we share the whole states throughout the complete store. Then we set up the cell, we add it to the view, and we subscribe to it so that the store receives any updates. This is the actual application state. I went with something really simple here. We just have a counter with type int, and whenever something changes, the counter will be added, will be increased with 1, for example, and then the UI will be updated. You could add much more and different items to the state, but this is a very simple state. Then we have the cells. Up here we have a basic cell. We can also ignore this. This is just some UI stuff that we can ignore. And then here we have a count button cell. What it does is it sets up the cell basically by adding a button with a target action mechanism. It implements the state updated method and sets a new title on the button whenever it's pressed. And we have an action function which is called when the button is pressed. And what it does is it changes the application state count variable that we saw earlier. We saw it here. So this is the count, and basically we are just adding the count whenever somebody clicks the button. And then we have another cell. It's a text cell. It has a state updated method that is called whenever the state changes, and as soon as it changes, we update the string value in the view. So once we have all this in place, what we can do is we just basically create one of these forms with a particular state, which is our sidebar state here. We add two cells, which is the text cell and the count button cell, and then we return the view so that it's used. And when I run this, we get a really ugly window. And it has a button, and when I click it, obviously, the state is being updated, and the type, the other elements in the view are automatically updated too. And the beauty about this is that in the cell here, we basically have the associated type because we add it in the top, and we do that by basically, we can say state point count and then add something, because the type inference actually allows us to do that. And since everything works together so well, we can also just basically take this cell here and add it a second time. And now when we do that, we basically have 2 cells. And when we press the button, they all update at the same time because they're all connected to the same associated type. Oh, so that was the demo. Now I have a short wrap-up. Basically, when to use associated types. And there are really just 3 use cases that you can do. The first one is, as we've seen in the demo, when you want to use them as concrete types at the call side, which means when you have a type that is abstract, but when you actually use it in your code, you need to access the actual concrete implementations like we do here. We've seen a couple of examples of that. Another one is some of you or most of you probably know the Lisco substitution principle, which basically says that you can't use in a subclass a more specific type than in the superclass. So in this case, we have an animal which has a food, and we have a cow which is an animal, but it's being fed with grass, and this doesn't work. And you can do that with associated types because you can basically define an associated type called food, and then you can easily say this is a cow, and this cow is an animal, and it takes grass, while another animal takes something else, which is of type food. And finally, associated types also allow you to model relationships for composition instead of subclassing. Thank you. If you want more information on this, there are 2 links where you can look it up, where more of this is being explained. And I'm also going to release a blog post at some point where I will have more examples that I couldn't fit into these slides. That's it.